images that comes from my research or what I plan to do in the future. And sorry, try to go in the wrong direction. So essentially what I'm doing in the lab every day, or trying to do in the lab every day, is to harness quantum phenomena for applications that spans both from fundamental to applied physics. So fundamental means understanding what and how quantum mechanics works, and applied physics is, well, using these tools to measure stuff. So I'm, what we say, it's an AMO physicist, which deals with atoms, molecules, and, well, optical physics, but photons. And this is what I mostly do, is I try to control atoms. Here are a cloud of atoms that I can move around. I try to control photons from lasers and sun. I made them interact, and I try to do cool stuff with photons and atoms, interaction between matter and light. And eventually, in my case, sometimes I may get out some molecule. That's not the focus of my research, but I have also this molecular side. For example, when I have two atoms that they collide and they have, by mistake or by chance or by whatever, by the property of the system, they will have an inelastic collision. So they stick together. Well, I got a molecule. On the other hand, there are also people that focus on molecules. And in that case, they usually use photons and atoms to control and get molecules. So that's the reason, I try to give a kind of reasons why the field where I'm working and many of us are working in, it's called AMO without a splitting. You're not an atomic physicist. You always have a part of the other components in your research. So the figures, the picture I'm showing you up here, they're coming from Dan's McCarran group that is also here at UConn. So it's next door in the office and also next door to my lab. And, well, just cool stuff.
Interesting.
So quick outline. Yeah. So as I said, the scientific goal is to control many-body quantum systems for application fundamental physics or applied physics. I will start with an introduction. What an atomic sensor, what is quantum metrology? I will introduce the concept that's very important for my talk of a standard quantum limit and how to go beyond this limit, which, as we will see, it's not a fundamental limit. I will list two recent results that we mostly got at MIT, and then I will show some perspective. So here is a picture of a setup with a lot of, at least two lasers that are in the visible wavelength turned on, which looks interesting and cool. Here is a system from farther away where you have this nice box to keep everything clean and more or less at a decent temperature or constant temperature. So let's start with, what does an atomic sensor sense? So an atomic sensor essentially measures, whatever atomic sensor you're using, the frequency that is associated with the energy difference between two energy levels in an atom. So there is a very important formula from quantum mechanics that relates the frequency to the energy. And it's just the frequency is proportional to the energy, and the proportional factors is this h, that's a Planck constant. And essentially, by measuring some frequency, you get an energy difference. And as I draw here, this energy difference between these two levels that we can measure in quantum mechanics, it depends on some field A, is very general here. And this A is the quantity we would like to measure. So if A changes, the energy difference changes, and so it changes also the frequency. And that's what essentially every atomic sensor is doing. Yet an example is, for example, magnetometers, atomic magnetometers, where the difference, the splitting between these two levels is proportional to the magnetic field. In atomic physics terminology, these are Zeeman sublevels. because it's something that's a phenomenon that has been discovered by a Dutch physicist in the end of, I think, 2 centuries ago, Simone. And well, here is an example of a sensor I built. There are some atoms in this cell in here. I interrogate them with a laser, and I'm able to measure the frequency difference between the split between these two levels, so the energy splitting. And actually, this depends on the magnetic field, and you can have many possible applications. One application, the first one I put here, is even not an application where you're measuring magnetic field. This is, let's say, it's a group of people that have set up and synchronized a network of atomic magnetometers all around the world. And what they hope to observe at some point is they would like to observe the Earth going through a domain wall in the axion field. What does it mean what I'm saying here? It's some of the possible theory that would explain dark matter, that we don't know what it is. It says that this dark matter may be composed by axions, which is a very special kind of field. And in a certain part or a certain theory, it says that the universe contains domains of these axions where you have different densities of axions. And eventually, atomic magnetometers would be sensitive to a change of this intensity. Because in this theory, these axions, they couple with a property of the atoms that could be detected with, that is affecting the Simone sublevels, whatever. It's just to say that this is a fundamental application. Try to see something that we never observed before with atomic magnetometers. There are more specific applications or easier to explain and motivate is, well, we're measuring magnetic properties of magnetic materials. Like here, I'm measuring the magnetization curve of a fluid that contains some iron. You can use atomic magnetometers to map magnetic fields. So when you can map magnetic fields, you can even map the magnetic field produced by your heartbeat. When your heart is beating, there is some current flowing around, and it creates a magnetic field. And by looking at the pattern of the magnetic field that is produced, you can get more information about the state of your heart compared to just measuring the current. So potentially there is some good reasons to do this for to detect heart problems before they become too dangerous. Or you can even use it to measure the magnetic field produced by your thought. So when you're thinking, you have currents flowing in your brain, and you can study different waves by measuring the magnetic field produced by your brain. This is one example where this has been done. And I think it's pretty cool and impressive. It's not me, but they did it. So then when we ask how really specifically an atomic sensor works, for this one, I will need to introduce a little bit of formalism, or a concept that is present in atomic physics. And essentially, we have our 2 levels that we want to address. We can depict them in these spheres that are called block spheres, where we can represent the population up and down and the phase between the 2 populations. So what we do with an atomic sensor, we send a pulse that's near resonant with this transition. We prepare an atomic state in a superposition of being up and down. The red arrow in this indicates the state. Then you let the system evolve in the presence of the field, and it will gain a certain phase. And at the end, you measure how much phase you gained. That sequence is called Ramsey sequence. And by the phase that you accumulated, you get information about how big or about the value of your field that you'd like to measure, A here. There is a problem, is that if you do this with a single atom, at the end you're going to measure, and the quantum mechanics tells you, well, whatever you do, you perform your measurement, you either measure or the atoms spin up or spin down. So you don't get a lot of information about your phase accumulated if you do a single measurement with a single atom. What you need to do is to perform this measurement many times and get some statistics. So instead of repeating the same measurement tons of time, what you do is we use more atoms at the same time. We prepare all of them together. And in that case, you can get the statistics all together and at the same moment. And instead of representing the state as an arrow on a sphere, we use a blob. This blob here represents the collective state of all the atoms. And the width that you see here is the so-called quantum projection noise. So this means that when I'm performing my measurement, even if I repeat the same experiment, because of quantum mechanics, I will get a certain uncertainty, and this certain uncertainty is depicted by the size of this sphere here. When you do your measurement, you get a Gaussian distribution where the standard deviation, so the uncertainty goes with 1 over the square root of n, where square root of n is the number of atoms you're using. You can use infinite atoms, ideally, and you get no uncertainty when you perform your measurement. Of course, you cannot use infinite atoms. Number of atoms is finite. And moreover, if you have too many atoms together, you can imagine that you need to compress them in a very small space. You get interactions, and it's going to be an interesting physics because you can study interactions and collisions, but it's going to be very bad for sensing. So the better picture is using this blob here. You let evolve the system, you get a phase. And so the best you can do when you perform one sequence is to get an estimation of your phase with an uncertainty of 1 over square root of n. So this limit is, okay, sorry, went too far. Just to give a things, we have atomic sensor here. I give a list. So we saw magnetometers. Magnetometers, they usually work, atomic magnetometers with 10 to the 10 atoms. So it's a lot. The uncertainty is quite low. Or I have also this N1 to 10. It's where you use kind of synthetic atoms in crystals. So it can be low here. So you have electric field meters, so you can measure electric fields. They use a little bit less atoms, but the same quantity. It's a lot of atoms anyway. Then you get gravimeters, where what you measure is G, the acceleration, gravitational acceleration, G. And in that case, they usually use 10 to the 6, 10 to the 5, 10 to the 6 atoms. So in this case, you can see already that the uncertainty on your phase measurement is going to be the 1 over the square root of this. So it's a milliradians. Milliradians is something you can think of based on what you can detect. So it's going to give you a limitation. And other things are clocks. Clocks are also sensors where the splitting ideally doesn't depend on any external field. So you get a constant rate of decaying, that frequency basically that defines a time. And here you span the number of atoms you have is between 1, because you have ion clocks where they use a single ion, to maybe 10 to the 4, close to 10 to the 5 maybe sometimes, because you don't want to have any interaction between the atoms. And so here you can see that it's already in the order of 10 to 100 milliradians, the uncertainty when you perform a single measurement with all these atoms. So there is a limitation when you perform your measurement. And the question is, do we need to go beyond that? Do we need to improve our sensors? And why, if so? So if you improve any sensor for metrology, you can get new opportunities. Here I list some opportunities that we can get if we improve the clocks we have nowadays that define time. So you get a better time standard definition, which allows you to perform operation faster. Because, for example, when you're on trade market, you need to know precisely enough who bought something when and who sold something when. And then there is a limit on the bandwidth of how fast you can do this. But if you measure times better, you can make it faster and faster. Then localization and navigation. GPS systems, they rely on very precise clocks. But if you can get a better clock, then you can get a better localization of whatever you're tracking. On the other hand, you can also start thinking of inertial navigation, where you start at time 0, you know exactly where you are, then you measure acceleration, velocity, anything you can measure, and time very precisely, then you can track your movement on the surface of Earth, so you know where you are without the need of GPS connection. That may be good when you are in somewhere underground or someplace where, yeah, GPS is off or whatever. Now, there's also a huge interest in quantum computing, quantum network, and a good definition of time and phase. It's critical to get quantum device working at a realistic scale. And then there's also fundamental physics beyond that. Here I have a picture of the first picture of a black hole that has been taken. They did it by connecting, synchronizing together many telescopes all over Earth in order to have an effective huge lens that had the size, almost the same size as Earth, that allowed them to see a black hole that's pretty small. But to do this, I said the term synchronize. So you need to synchronize all the telescope in a very precise way. You need to use clocks. If you have a better clocks, you can synchronize these telescopes better, so you can observe the sky or the telescope or the black hole, whatever you want to observe, for longer, and you can again gain a lot of more information and resolution what you're observing. Another thing is for clocks is measuring gravitational effects. So recently it has been measured. So Einstein theory, general relativity, says that essentially due to the curvature of the gravitational field, the time flows at a different rate. So essentially, if you're here or here at a different in height, there is a slight difference in the curvature of the gravitational field, and the time flows at a different rate. You may have seen the movie some years ago, Interstellar. At some point, someone goes close to a black hole, someone stays on the vessel. These guys that go down close to the black hole, they stay there in their time frame for 15 minutes. When they come back, the other guy aged by, I don't remember, it was 40 years. That has been calculated. And that's an effect that actually occurs in general relativity. So it has been measured. And here with clock, it has been measured, this effect at the distance of 1 centimeter and 1 millimeter in these two papers here, that they came out at the same time, the same thing. So it's very tiny distance, so almost microscopic distances. And also, if you're interested, you can calculate on the back on the envelope what this means for you. So over the course of your life, more or less, your head or the cells in your head are going to be 80 nanoseconds older than the cells on your feet, which is not a lot, but it's still a difference. Yeah, that was a lot of things. So now I need to introduce what is quantum metrology. This is the classical, the standard way of doing atomic sensors. So you create your state, you have this blob that limits your resolution, and you get your measurement at the end that's limited by 1 over square root of n. The quantum metrology basically introduces an extra step at the beginning. You let the system evolve, or you prepare the system in a so-called entangled state, where the atoms have quantum correlation between each other. And you can engineer this state so that in your quadrature or direction of interest, you can have this noise reduced. Like in this case, it's squeezed. And if you do so, you can, using this entanglement or quantum correlations between atoms, you can reduce the uncertainty on your final readout, which allows you to get a better sensor with the same amount of resources. Resources means the same amount of atoms. So to do this, you need a step. It's just one extra step, but it is the fascinating one and maybe the most complicated one in this thing. And you need a so-called nonlinear Hamiltonian. A nonlinear Hamiltonian, so a Hamiltonian is describing the evolution of a system. So a nonlinear Hamiltonian is an evolution of a state that depends on the state itself. So that's the meaning of nonlinear. So there is a self-interaction somehow. And to do that, you need to have an atom-atom interaction. So you need to engineer or have, by nature, some atom-atom interaction. But for sensing, there's a problem. When you're doing metrology, as I said before, we're trying to keep the number of atoms low enough so that there is no atom-atom interactions, but here you need atom-atom interactions. You can think of an analogy why I don't want interaction is when you have a pendulum. Okay, you get a pendulum, it's fine, it swings and you can measure time. You can have two of them just to average out some problem, but if you put them too close together, they start to collide. And if they start to collide, you cannot measure time with these two pendula because it's a random interaction, random process. For atoms, it's very much the same. So the question is how we can do this. So we want atom interaction when we are preparing the state, and we want to turn off this interaction later. So very much like we turn on and off light, we would like to turn on and off the interaction. And indeed, what we did in our groups, and we're doing also in our group, is to use light, induce interaction between atoms, so that you can turn off this light and the interaction is gone. And this is done and is achieved by having a cavity, so two mirrors around the atoms, where the light goes in, bounces back and forth in the mirrors many, many times and interact very likely with all the atoms, so that you can, when you turn on your light, you turn on the interaction between the atoms. You turn off your light, the photon eventually leaves the cavity, and then you have no more interaction. You get your state, and then you can start your sensing process. I will skip the details on how it works. I think it's not really giving you a lot more. So using this introduction, so we'll go and list a couple of recent results we had. So the first result is about entanglement-enhanced ytterbium optical clock. So ytterbium is an atom that has two valence electrons, so it has a certain structure in its different levels that you can use. And here I'm listing the three most important, two that are used to trap the atoms and cool them and control them, which is the blue and green line transition here. And then there is the very interesting one. It's a transition that's called the clock transition. Basically, we're measuring the splitting, the energy difference or the frequency associated with this energy splitting between these two levels that has a huge Q factor. A huge Q factor means that when you let the atom oscillate somehow at this frequency, you will get 10 to the 15 oscillations before the atom decays to the ground state. 10 to the 15, it's a lot of oscillations. And here it's compared to RF clocks, radio frequency clocks. That's the standard nowadays. That's the defining time where you have roughly 10 to the 10 oscillations only. It's still a lot. It's 10 billions, but it's factor of 5 lower. And here I'm showing the fractional precision of clocks versus years. And these, for now, the blue are just radio frequency clocks, so cesium clock. These clocks that I'm listing here, well, not the best one, but you can buy and order clocks based on radio frequency transition nowadays. But essentially, this is how they improved from when they have been invented near the, well, now it's a lot. It's 60 years ago, more than 60 years ago, to nowadays. They reached 10 to the minus 6 in fractional precision. But when I put on that clocks that are trying to measure optical transitions like the one here in ytterbium, these are recent results, and there is a faster improvement. They profit from the fact that they have much more oscillations that they can measure in 1 second. And here are the two most recent results where they got a fractional precision dipping below the 10 to the minus 19, so reaching 10 to the minus 20, which is kind of impressive. But there is a but. It's that there is this solid black line that I put here. And this solid black line that I put there is essentially the fact that these people that achieve this high stability or fractional precision, they basically reach the standard quantum limit. So the dashed line showing here is the expected standard quantum limit. The blue line is representing what they got. And here, a little bit of context. This is Allen deviation plot. It tells you, basically, when you repeat your measurement or when you measure longer and longer your quantity, you gain more information about the time. So this is the uncertainty of your measurement. And the longer you observe something, the more information you get it. So that's what you will get. And essentially, you see this is the best precision they got when they average their, or they observe, they measure, let's say, time flow for, this is what, maybe 6,000 seconds. So it's a lot of time, but they got this. So they reached this limit. We want to go below that, beyond that. And that's what we did with our turbulent clock. We demonstrate that that's possible. We first shown that we can get a state, an entangled state, where the variance, the uncertainty that we are measuring, shown here, dips below the standard quantum limit. So the horizontal line here, blue data, are obtained when we do nothing to our atoms, no interaction, no entanglement, no quantum correlations, and we get something around 10 to the 0, which is 1. It's normalized to it. If we generate this entanglement, so quantum correlations, when we perform our measurement, we dip below that by a certain amount. In this case, it might be kind of 3 times below that. So there is entanglement. We can reduce the projection, the noise, those things. So we perform a clock operation. We measure time with a not super performant clock, but anyway, near its standard quantum limit. And we did it with a state that's non-entangled and a state that's entangled. And we see that we got a 4.4 dB of improvement, which means we improved it by 2.8 times. So this means that when to reach the same stability, you need to measure something 2.8 times shorter or faster. And it may not look a lot, but you can always compare this 2.8 times to your salary. So an increase of 2.8 times in your salary is a lot. A decrease 2.8 times if your salary is even worse. I mean, it looks even larger, I guess so. And what we have here is that we'll introduce the next step is that the improvement here, it was just limited by the final state readout, which means that when we were measuring at the end, we didn't have, let's say, good eyes. We were not able to see anyway all the atoms. We get some fuzziness due to the fact that we were not able to measure it well anyway. So the question is if we can go beyond that limit, and we use something that's called time reversal based quantum metrology, which looks cool because there is time reversal. And indeed, I will show you what I mean with time reversal and how it works. But first of all, I'd like to introduce a big concept. There's a little bit virtually now. So the question is how to improve metrology. So far we said, or I said, well, there is this standard quantum limit. There is a certain noise. Let's reduce the noise, and then we get a better sensor. Is that the only way of doing it? So, well, not really. The sensor performance at the end is defined by its signal to noise ratio. So the quantity you want to measure divided by, so the signal, phi, divided by the uncertainty of phi, and phi. And let's assume you are trying to target a car in Manhattan. I use Manhattan because it's an example of US cities where everything, all the streets are linear and nice and square. And you have 2 cars and you want to target one of these 2 cars, and your GPS signal is not very good. So here I have 2 blobs, 2 uncertainty. So you don't know which car is where. So you have a high chances to get the wrong car instead of the right car. So what you can do is, well, if I reduce my noise, I can see the 2 spots and I know that my car is here. That's great. Is that the only way to improve my signal to noise ratio? Of course, it's not. When here I reduce the noise and I got a better signal to noise ratio. What I can do is I can increase the signal and get a better signal to noise ratio. And here I give you another example. If it happens to you to travel to US all the towns and cities here are squared and boring, but then you go to Boston and that's not. And in that case, it's highly nonlinear system in Boston. So here, our signal between the two cars is the distance between two cars. Okay, so here I have two cars, two different streets, and the distance is much smaller than the uncertainty. But if I evolve the system, I let the cars keep going in their street, I will see that if I wait a little bit under this highly nonlinear system, the two cars will split out and the distance between the two cars becomes huge, right? One way goes in one way, the other one goes in the other way. So without improving my GPS signal, I can now target the right car because I increase the signal, which is the separation between the two cars. Now the question is, well, one can see these trees as field lines of a nonlinear Hamiltonian. But the question is, what happens if I have a quantum car? So the quantum car is one, or there are two cars, but this fuzziness is not my GPS, but it's the fact that the cars are simultaneously in different streets. So if I let my system evolve under this Hamiltonian, I will get a certain probability to see the car here, here, or there. I let go the second car. Sorry, let evolve the second car, and the same thing happens. So I also increase the noise of that thing. So I have no increase in signal to noise ratio. And that's quite obvious from quantum mechanics, because if you have unitary evolutions, the overlap just doesn't change. So the question is, can we amplify signals in the quantum realm? And there is a way. So here I have a more realistic system. So when it's classical, I have dots in some space. I let this system evolve under a nonlinear Hamiltonian, where depending on its vertical positions, it goes faster and slower. And if I wait long enough, I get a certain separation where I increase the signal. For quantum mechanics, if I do this, I will shear my stuff here. So I will not gain a lot. I get also much larger noise in the horizontal direction. But if I can evolve the system backwards in time, so I apply my signal here, I displace vertically, this little thing has been displaced vertically, and I evolve it backwards in time, I will get two nice distinct blobs that I can detect. So I increase the signal. And how you evolve backwards in time? Well, evolving backwards in time, if you have a certain system that's closed, it's equivalent of changing the sign of the Hamiltonian that's governing the evolution. So you're just evolving backwards. And that's what we can use to enhance the signal to noise ratio also in quantum mechanics. That's indeed what we did. I'm not showing the thing here, but essentially we can do this by changing the frequency of laser light that's creating the interaction. We can change the sign of the Hamiltonian that's generating the entanglement. So here I have a certain plus H. We apply a certain phase. We generate this entangled state. We apply a certain signal and then evolve backwards in time by just changing the frequency of the laser that's addressing the atoms. And when we do that and we measure the signal versus the displacement, we see that we have a huge improvement. How we see that? So here is on the horizontal axis, we show the displacement we introduce in terms of radians. And the black line shows you a one-to-one slope, which is what you would get if you do no entanglement, nothing special. If you move something, rotate something by a phi, you would detect a rotation of phi, right? And the red one are our data. So we got a rotation that is amplified by a factor of 5 or more, which is significant. So you get a huge increase. And when we use this technique to perform an enhancement in our sensor, we see that when we operate it at the standard quantum limit, we are here. When we apply our time reversal protocol, we can get an improvement of 15. So 15 is 5 times larger than more than 5 times larger than the 2.8 we got earlier. And here, 15, it's already clear that's a lot. I'm not going to use any example like money or salary, because a factor of 15 is huge for that end. But you can think in another perspective, from a scientist perspective, let's assume you want to measure something very exotic, very hard to measure, and you start your experiment nowadays and you say, oh, I need to measure for 60 years to get enough data and enough resolution to detect this effect. 60 years is more than a scientific career of anyone, right? You start when you're already 20 years old, so 60 years is a lot. It's a lifetime project. But with this improvement of factor of 15, a lifelong project becomes just, I will put something like that, just PhD time. So it's a huge improvement in time, and it can save time and can measure more things. Another little trick that you may want to learn if you're doing science, then you have improvement. If the factor of improvement is less than 10, it's better if you express it in dB because the number is larger. If it's larger than 10, the improvement, then you would express it in kind of linear scale, because 15, a factor of 15, I think it's 11.2 dB or 11.5 dB of improvement, while the previous example I gave you, it was a 2.8 factor of improvement, but if you express it in logarithmic scale, so in dB scale, it was 4.4, and 4.4 is larger than 2.8, just for a mind. It's just a trick, marketing trick. Yeah, now a little bit of perspectives, but first of all, I have a story, something that happened in the lab I was working. So I tried to use AI in the lab just to optimize some parameter. And it was in an experiment. It's called the Rydberg lab. So the goal was to optimize the number of atoms loaded in our system. So we said, okay, we can tune all the parameters by hand, or we can use some automatized way and some simple AI or artificial intelligence to optimize the parameters. So we set up the experiment, we set up the cost function and everything. So with a machine learning system that's changing all the possible parameters we could change to load more atoms. And we left the system running for a couple of hours. We went for lunch. Then when we came back, we observed the system and we saw that by optimizing the number of atoms, we got more atoms that we could do on our own, and we got a Bose-Einstein condensate in a lab. So Bose-Einstein condensation is something can be done nowadays. It's done worthwhile, but it's hard, and it's something that gave basically won the Nobel Prize in 1997 because they created the first Bose-Einstein condensation. It's a big machine. So we were kind of surprised, and we figured it out that it was not just optimizing the number of atoms that allowed us to get the system to get a BC, Bose-Einstein condensation, was also the fact that we made a mistake. And the mistake was that, well, it was all-light induced. Oh, sorry, yeah, this is the thing. Sorry, when you would say that's been proposed by Bose, the same Bose as Bose.X, and Einstein 70 years ago. So it's not 70 years ago, 100 years ago. It took 70 years to get these Bose-Einstein condensations in the lab. They used very advanced methods. And in our case, a computer with a couple of things got a Bose-Einstein condensation by mistake, because actually what we did is we had some lens misaligned that was creating a very weird pattern in the light field that was trapping atoms. So it was a mixture of human little mistake or happy mistake and the power of AI. But from this one can learn that AI is going to be useful to improve and optimize systems. And if you still but you need still to put a little bit of humanity in that, and that one can have a little bit of inventive, if you want, or mistakes, because humans do mistakes, right? And sometimes mistakes are very good to learn and discover new effects. So I go back to Outlook, and that's just a quick overview of what I plan to do and I'm doing here nowadays. Is that I like to add a little bit of extra control to what we already achieve with cavity and atoms. So cavity and atoms allows you to get basically a programmable and controlled atom-atom interaction, as we saw. Turn on the light, turn off the light, choose the frequency, you can get the interaction you want within the atoms. There is a new technology that's taking over now, and it's optical tweezers, where you can control and trap single atoms. So you can have single individual atoms, you can put them where you want, you can control them individually. So in that case, then you get a single atom control and atom-atom interaction control. It's an extra knob. And when you have an extra knob, you can perform more experiments. One possible experiment is we have clocks, atoms put at a different height. You have gravitational redshift that it is possible to be measured. If you can generate entanglement with the cavity within these atoms, then you would have a system that is sensitive to two effects. One is entanglement that comes only from quantum mechanics, and another effect that's a gravitational redshift that is predicted, and actually it exists and it comes and it can come out only from the general relativity theory. So it's a system that is sensitive to two very successful theory that no one so far was able to unify, which is cool. Another thing is that we can go ahead and do some more quantum simulation and have access to the complete Hilbert space. Hilbert space describes all the possible state of a system of n atoms. So you can study exotic quantum states, you can investigate and see whether there is some quantum chaos stuff. You can do quantum simulation. I could put quantum computing also, but companies are doing it, so it's not where I want to go. So as a quick conclusion, I'd like to understand how our universe works. And well, we started doing it. We can do and improve everything and get more information about everything and study more stuff by adding knobs to our systems. So namely here, getting control of single atoms and atom-atom interaction in a very precise way. And I'd like to maybe give you a bit more pragmatic perspective before concluding. So I took this paper as an example. So it's in Nature Physics one, time reversal-based quantum metrology with many-body entangled state. And one may wonder, well, where are all these people now, right? I mean, not all, they're not many, but what they're doing. So, well, I'm the luckiest one. I'm here, I'm still doing physics. I am doing AMO physics, I'm doing similar stuff, and I'm now an assistant professor, which is great. But it's not the only option. When you study quantum mechanics and you do stuff in atomic physics, AMO physics, you have a lot of other possibilities, very different from the field where you started in. So, well, that's my lab, blah, blah, that's what I'm doing. Another one, second name, Edwin Pedroso. He just started 3 weeks ago, also as an assistant professor. So that's boring in the sense that it's doing the same thing as me. But for example, we have the third name, Albert Yatulin. He is close to Ancul, I think, nowadays. He's in Paris, and he's a senior quantum engineer in a quantum computing companies called Quandela. Ziyang Li, he is now a postdoc, still in AMO physics, also a bit boring, but at Stanford, so it's another place. Enrique, so the first name here, the fifth name, he is a data scientist now in Las Vegas. Specify is doing finance, is not trying to trick casinos or stuff like that, but he could. So it's quite different. Chi was also a PhD student doing AMO physics, and now is an FPGA engineer. We were not allowed to know the name of the company he was working on. We know that he was doing ultra-fast trading, and he's in Florida. Ultra-fast trading means that what these companies are trying to do is trying to get to beat the clock of the market so that they could eventually buy and sell stuff before they actually change their value. So how the market works is there is some bond increase, the value of some bond increase. So it increases at the moment T1, the T2, this is updated in the system. And so this is the new price. So if you can detect this and send in buying or selling this bond before the system is updated, then you're doing an ultra-fast trading and you're gaining money because you know in the future what the value is going to be of your bond. And there are other destinations. There are many people working quantum computing companies like QERA. There is someone that is went to the Metrology Institute in Japan, University, JPL, NASA. Also, there is interest for quantum and atomic sensor, of course, for NASA. And then there is another example is Andrea Mooney that he did this PhD in the same group as Ankul, and he's now a quantum system engineer in Barcelona, Spain. And I can tell you, none of these people had a problem finding a position they had to look for, but they found a lot of things and they could actually decide what they wanted to do. That's a great thing of AMO physics. So yeah, with this one, I conclude my very long solo.